Hello everyone, today I will talking about self-compacting concrete SCC. For contents I have about 10 points to talking about SCC. Firstly I will define SCC and I will talking about history of SCC, comparison between normal and self-compacting concrete, properties of fresh SCC, materials used for SCC, requirements, different tests, mixed proportioning, advantages and disadvantages, how economical is SCC, and the uses of SCC, major construction uses SCC. Definition of SCC: self-compacting concrete, also known as self-consolidating concrete, is a highly flowable non-segregation concrete that can spread into place, fill the formwork, encapsulate the reinforcement without any mechanical compacting. SCC doesn't need any vibrations to fill the formwork. Development of SCC: self-compacting concrete, developed by Professor Hajime Okamura of Kochi University of Technology, Japan in 1986. During his research, Okamura found that the main cause of the poor durability performance of Japanese concrete structures was the inadequate compacting of the concrete in the casting operations. By developing concrete that self-compacting, he eliminated main cause for the poor durability performance of their concrete. By 1988, the concept was developed and ready for the first real-scale tests. The first real use of SCC was in 1988. Problems with conventional concrete: requirement of skilled worker for compaction in conventional concrete, difficult to use mechanical compaction for underwater concreting, cast in situ foundation, structures with heavy reinforcement. As you see in the right figure, heavy reinforcement structure, if we cast in conventional concrete, that cannot fully fill the formwork. Comparison between conventional concrete and SCC. For fine ingredients, normal concrete have about 12% and SCC have 18%. So more fines for SCC make it more workable. And we have same percent sand for two types, 24%. Coarse aggregate, we must decrease the percent of coarse aggregate in self-compacting concrete to make it more workable, 28% for SCC and 46% for normal concrete. And more water used for SCC, 20%, 18% for normal concrete. Admixtures, no admixtures for normal concrete, or little use of plasticizers, 0.01% admixtures used for SCC. Mechanism of achieving self-compactability: reduction of water binder ratio, limitation of coarse aggregate content and their maximum size, addition of mineral admixtures that lead to high segregation resistance of mortar and concrete, limitation of coarse aggregate content and their maximum size, addition of mineral admixture, usage of superplasticizers and viscosity modifying agent VMA that lead to high deformability of mortar and concrete. These achieve self-compactability. Limiting coarse aggregate increase deformability and segregation resistance and passing ability. Adding superplasticizers increase flowability, decrease liquid limit, and decrease segregation resistance. Reducing water powder ratio increase segregation resistance and decrease deformability. Properties of fresh self-compacting concrete. Self-compacting concrete must have three characteristics in a fresh state. The first one is filling ability. Flows easily at suitable speed into formwork. Passing ability. Ability to pass reinforcement without blocking. Passes through reinforcement without blocking. High resistance to segregation. The distribution of aggregate particles remains homogeneous in both vertical and horizontal direction. For vertical direction, static segregation due to gravity, and for horizontal direction, dynamic segregation due to flow. Materials used for SCC: cement, ordinary paste concrete of 43 or 53 grade can be used. Aggregate of size limited to 20 mm. Congested reinforcement 10 to 12 mm. Well-graded cubical or rounded aggregates. Fine aggregate can be either natural or manufactured and of uniform grade. Particle size is less than 0.125 mm are considered as fines. Water, it must be of the same quality used for that reinforcement concrete or pre-stressed concrete. Chemical admixtures used for SCC: the new generation superplasticizers, termed as polycarboxylated ethers, is particularly used. Viscosity modifying agent for stability. Air entraining agents to improve freeze-thaw resistance. Retarders to control setting time. Mineral admixtures, we have granulated plast furans slag GGBS to improve rheological properties. Fly ash to improve the quality of durability. Silica fume to improve mechanical properties, and stone powder to increase the powder content. Requirements of SCC: the main characteristics of SCC are properties in the fresh state. The mixed design is focused on ability to flow under its own weight without vibration. That is filling ability. And the retain homogeneity, passing ability without segregation resistance. A concrete mix can only be classified as SCC if it has the above mentioned characteristics. Deformability. SCC's paste theory explains the mechanism governing the workability of concrete. Enough paste to cover the surface area of the aggregate, and that SCC's paste surfaces to minimize the friction among aggregates and give better flowability. Without the paste layer, too much friction would be generated between the aggregate, resulting in extremely limited workability. So as we see in the figure, without paste, too much friction between aggregates, and with paste, the friction will be minimized. Passing ability. The probability of blocking increases when the volume fraction of large aggregates increases. The size of aggregates, their shapes, and their volume fraction influence the passing ability of SCC. The potential of collision and contacts between particles increases as the distance between particles decreases, which therefore results in an increase in the internal stresses when concrete is deformed, particularly near obstacles causing blockage. About segregation resistance is largely controlled by viscosity. Ensuring high viscosity can prevent a concrete mix from segregation and or bleeding. Bleeding is a special case of segregation in which water moves upwards by capillary action and separates from the mix. Some bleeding is normal for concrete, but excessive bleeding can lead to decrease in strength, high porosity, and poor durability, particularly at the surface. Different tests on SCC. We have so many tests on SCC to ensure the filling ability and passing ability and segregation resistance. For filling ability, we have slump test flow, T50 centimeter flow test, slump flow, V-funnel test, RMIT, G-ring test, L-box test, U-box, and fill box for passing ability. For segregation resistance tests, V-funnel at T5 minutes, GTM screen stability test. Slump flow test. The difference between slump flow test is same in normal concrete. The difference between D1 and D2 should be less than 50 mm, otherwise the test should be repeated. Spread flow diameter SF is equal D1 and plus D2 divided by 2. So the range of SF is between 650 to 800 mm. And another test on SCC, T50 centimeter slump flow test. T50 centimeter is between 2 seconds to 5 seconds. That's the acceptable range. V-funnel test. The V-funnel flow time is the period a defined volume of SCC needs to pass the narrow opening. This narrow opening dimensions is 65 square millimeter, as you see in the figure. Gives an indication of the filling ability of SCC provided that blocking and or segregation do not take place. The V-funnel flow time TV is the period from realizing the gate until first light enters the opening, expressed to the nearest 0.1 second. For SCC, a flow time of between 8 to 12 seconds is considered appropriate. RMIT test. RMIT test determines the filling ability. The RMIT flow time is the period defined volume of SCC needs to pass a narrow opening, a tube narrowed by orifice. The slow time of the RMIT test is to some degree related to the plastic viscosity. The RMIT flow time is to the period from realizing the gate until first light enters the opening, expressed to the nearest 0.1 second. Acceptance criteria for SCC is between 0 to 5 seconds. G-ring test is a test used in conjunction with a slump test to assess the passing ability of SCC through gaps in the obstacles. Example of obstacles is reinforcement. For this test, the slump test apparatus is used with an open steel rectangular section ring with 16 steel rods with 5 16mm and 100mm heat. The gaps between the bars is 42mm. Spread flow diameter SFJ D1 plus D2 divided by 2. For spread flow diameter, if the SF less than 25mm, the passing ability rate is 0 and no visible blocking. If the SF between 25mm and 50mm, the passing ability rate is 1 and minimal to noticeable blocking. If the spread flow diameter greater than 50mm, passing ability rate is 2, noticeable to extreme blocking. L-box test is used to assess the filling ability and passing ability of SCC, or in the other words, the ability of concrete to pass through reinforced bars without blocking or segregation. After filling the vertical column of the L box, the gate is lifted to allow SCC to flow into the horizontal part after passing through the rebar's obstructions. Two measurements are taken: H1 and H2 heats of concrete at the beginning and the end of the horizontal section, respectively. The ratio H2 divided by H1 represents the filling ability, and typically this value should be 0.8 to 1, while the passing ability can be detected visually by inspecting the area around the river. U-box test is used to measure the filling ability of SCC. Fill the vertical section of the apparatus, lift the sliding gate. After the concrete has come to rest, measure the heat of concrete in the compartment that has been filled. In two places and calculate the mean H1. Measure also the heat in the other equipment, H2. Calculate H1 minus H2, the filling heat 30 mm maximum. If the concrete flows as freely as water, it will be horizontal, so H1 minus H2 is equal 0. Therefore, the nearest this test value, the filling heat, is to 0, the better flow and passing ability of the concrete. Mixed proportioning of SCC. Coarse aggregate less than 50%. Water powder ratio 0.8 to 1. Total paste 400 to 600 kg per cubic meter. Sand content greater than 40% of mortar and less than 50% of paste volume, and greater than 50% by weight of total aggregate. Free water less than 200 liters per cubic meter. Paste is greater than 40% of volume of the mix. Advantages of SCC: reduced permeability and improves quality, durability, reliability of concrete structure due to better compaction and homogeneity of concrete. Ease of placement result in cost saving through reduced equipment and labor requirement. Less noise from vibrators and reduced danger from hand-arm vibration. Greater freedom in design. Improves working condition and productivity in construction industry. Faster construction. Elimination of problems associated with vibration. And the disadvantages of self-compacting concrete are more stringent requirement on selection of the materials, lack of globally accepted test standard and mixed design, costlier than conventional concrete based on concrete material cost, exception to placement cost, more precise measurement and monitoring of constituent materials. How economical is SCC? There is a feeling that cost of SCC is much higher than that the corresponding normal or high strength concrete. It is seen that the materials of self-consolidating concrete is about 10 to 15% higher than normal concrete. If one takes the other components of cost such as cost of compaction, finishing, etc., then one would realize that SCC is certainly not a costly concrete for comparable strength. Uses of SCC: complicating reinforcement, raft foundation, pile foundation, retaining wall, repairs, restoration and renewal. Major construction uses SCC: Burj Khalifa in Dubai, United Arab Emirates, 2010. Södra Länken in Sweden 1997, Delhi Metro Project in India 1998 with length 348 kilometers,